Hey, my name is Bahi Watson, and this is my other video on PN junction diodes used in rectifier circuits. So again, it's a 15-minute presentation, and I'm assuming that I'm working with community college students. So what is a PN diode? Okay, a PN diode is a two-layer semiconductor with the boundary separating the P layer and the N layer. Okay. Um, The N layer is the cathode, right, and it's negative charge, and the P layer is the positive charge anode. Okay. Um, PN diodes allow electrons to flow in one direction and are synonymous with check valves in fluids. Okay. So in the first picture that you see, um, this first diode is actually forward biased, right? Just because we have the positive side of our voltage connected to the positive side of the diode, right? Um, and we have the negative side of the voltage connected to the negative side of the diode, right? Okay. So let's take a look at what happens when it becomes reverse bias. All right. So when we have it reverse bias, we have no flow. Okay. So we have the positive side of our voltage connected to the negative side uh, of our diode. And then we have the negative side of our voltage connected to the positive side of our diode. And what this does is it creates this depletion region here. Okay. So in the first forward bias, you can see that on the positive side, um, when I connected the positive side of my voltage to the positive side of the diode, um, they repelled each other, right? Closing that depletion region. Okay. But when I get over to my reverse bias condition, right, when I put the positive side to the negative side, they actually attract, which creates this depletion region. Okay. So here we have a curve here, just showing. This curve basically just shows forward biasing and reverse biasing, right? So if we take a look on the reverse biasing, right? So basically, you can prevent current from flowing, right, up to a certain point, up to its breakdown voltage. Okay. Once you pass that breakdown voltage, right, um, you start to increase, right, and you can get to where you permanently damage the diode. Okay. Uh, Also, right, um, on the forward biasing side, right, you can actually have a threshold voltage, right? So as long as you pass this threshold voltage, right, you can have current flowing in one direction, okay, until you get to this until you permanently damage it, right? So there's a current in which you can permanently damage um, your diode when you're forward biasing, okay. Now, basically what I'm saying is over here is that the threshold voltage is normally about 0.2 to 0.6 volts in most diodes, right? The graph doesn't have a consistent scale on the y-axis, right? And many times, and many diodes may have a magnitude of the reverse bias breakdown voltage to be as much as 100 times the magnitude of the forward bias threshold voltage. Okay. So basically what I'm saying is that this is not the scale. Okay. There are different types of diodes. You have signal diodes, also known as high-speed diodes or switching diodes. Um, they're typically used to process information in circuits, right? They have fast response times due to their low junction capacitance, and they're not designed to withstand high current. Okay. The second picture that you have is a rectifier diodes. Okay. They're physically larger, right, than signal diodes, and they're built for high currents, right? So because they're built for high currents, they're not suitable for fast switching. Okay, and some of them may also include a heat sink. Also, I wanted to point out that on most diodes, when you have this line here, right, this line will be representative of the cathode side. Okay, and also you have these xenodiodes, right? They behave similarly to a signal, a rectifier diode, but they have a lower breakdown voltage, and they're really intended to be used for reverse biasing. Okay. So again, I have a circuit, right? And on the left, I'm showing the one circuit on the left is forward biased, and the one on the right is reverse biased. Okay. So again, you can see the voltage is connected to the positive side of the diode, right? And you can see that my multimeter across that diode is reading 0.7 volts, right? But when you look at the multimeter at the load, you're reading 5.3 volts, and that's just due to losses at the diode. Okay. But again, if you look on the right, you can see where you have this reverse biasing, right? And when you look at the voltage across your load, you have 0 volts. Okay. So let's take a look at some applications of biasing, right? So this first picture at the top, I actually have 2 diodes, right? So these are, I can have 2 or more outputs from a logic chip, right? And you can see that it's connected to this LED, right? So basically what this is being used for is to protect the chip from any backflow of current, right? Just in case you don't want to damage your chip and you don't want to have any backflow of current, you can use these diodes, okay? And this one is actually forward biased, okay? So here I have a rectifier diode that's placed across a motor, right? And it's a motor that creates a spike of reverse voltage when switched on or off, right? So basically what I'm trying to do is use the reverse biasing to protect all the other components in the circuit, okay? So now I want to talk about rectification, which is the most popular application of the diode, okay? So rectification is the conversion from alternating current to direct current, right? And it requires the use of a device that only allows the flow of electric charges in one direction, which is a diode, okay? Now, before the development of silicon diodes, right, folks would use vacuum tube rectifier stacks. And these vacuum tube rectifier stacks are nearly obsolete. Okay, so what I have a picture of a vacuum tube rectifier from the 80s, and it may even be earlier than that, maybe the 60s this is from. And this is just a book on vacuum tube rectifiers, copyrighted in 1958. All right, so the simplest way to reduce power to a load, right, is to do half-wave rectification, right? But it's inefficient, okay? You have AC power supplied to the load, and as you can see, right, you're only getting 1/2 of every cycle to the load, all right? So it's very inefficient, okay? All right, here I have a circuit that I created in Tinkercad circuits, okay? Here you can see I have my function generator, right? And I'm going to start my simulation, right? Now look at what I'm reading from the oscilloscope, okay? So the oscilloscope, where I have my voltage introduced, right? You can see the sinusoidal wave, right? But at the load, right, you actually just see half of those waves, right? So let's go in and count them, right? So you have 1, 2, 3, 4, right? So I have 4 waves, sinusoidal waves, right? and I have 4 peaks. Okay, so I'm basically able to take advantage of half of that wave. Okay, and this is forward bias, by the way. I believe it's playing again. Same one. Yeah, it's the same one playing again. Okay. All right. So now I want to talk about full wave rectification, right? So remember before we were only taking, we were able to use half of that sinusoidal wave. Now I want to take advantage of both half cycles of the sine wave. Okay. So there are a couple ways to do it, right? One, I can use a transformer, right, which is called a center tap design, right? So I can have a transformer with a center tap and secondary winding and 2 diodes, okay? Or I can use a full wave bridge rectifier that uses a 4 diode bridge configuration, okay? And basically, as you can see on my multimeter, right? So I have this AC voltage coming in, right? I have my full wave bridge rectifier, right? And what my multimeter is showing is that now I can take advantage of the full wave, the full sinusoidal wave. So if you count here, 1, 2, I have 2 peaks, 2 troughs, right? So now I have 1, 2, 3, 4 peaks at my load. Okay. So I also created this in Tinkercad circuits. Okay. I'm gonna start the simulation. All right, so this one is at 4 hertz. I have 10 volts coming in, right? And you can, what I'm doing, I'm counting actually the peaks and the troughs, right? And I have 4 peaks, 4 troughs, and now I have 8 peaks at my load, okay? So I'm able, this full wave bridge rectifier allows me to take advantage of the full sinusoidal wave, okay? I'm able I'm able to change this from AC to DC current. Okay. Go to the next one. All right. This is the same circuit, but I changed the frequency. So now it's at 10 hertz, right? So you can see that I'm still taking advantage of the full sinusoidal wave, right? I increased the frequency, so you don't see that the light shutting on and off like it was just because I increased the frequency, even though it still is, but not to the human eye. Okay. So let's talk about the current flow in a full wave bridge rectifier. Okay. So basically, what you see here, right? So 2 of the diodes I can use, right? And I can take advantage of the positive half cycles. Okay. All right. Where on the bottom, I'm taking advantage. Well, let's start with the top. Okay. So I have my AC voltage coming in, right? And it's coming in and it passes through this diode, right? It doesn't go this way. Why is that? Because this would actually be reverse bias, right? It would be reverse bias. So no current is flowing through this direction. Okay, so it flows through here, right? Neither through here. Doesn't flow that way either, right? Passes through our load, right? So it passes through our load, right? And then it returns, right? Comes back around through this diode, right? So it doesn't go through here. right? It goes back through this diode, right? And it comes back to our source, okay? So in this top picture, I'm able to take advantage of the positive half cycles, right? But how can I take advantage of the negative half cycle, right? So basically, if you take a look at the current flowing in the opposite direction, right? Now I can utilize those two diodes that I didn't utilize in the first picture, right? So you can see the current flow flowing in this direction to this diode through my load, right? Is flowing into this other diode, right? And flows back to the source, okay? All right, so I would have a class exercise, right? Kind of running out of time, but well, my time is up. My 15 minutes are up. Wondering if you can modify the full wave bridge rectifier that I did in Tinkercad circuits to only send current flow for the positive half cycles, and then modify the full wave bridge rectifier so that the load receives current flow for the negative half cycles. And then just let me know if the graphics on the multimeter are correct. If not, how should they look? Okay. So here's the answer, right? So basically, this is my simulation for the positive half cycle, right? So I have my positive charge going through this diode, right? Through my load, right? It comes back around, comes back to the source, okay? Back here, back to the source. All right. All right. Let's see that. See if we can see that one more time. And you can even count the peaks, right? Count the peaks and the troughs again. 1, 2, 3, 4. 1, 2, 3, 4. Right? Okay. So I'm only using half of that. Here's the answer for the negative, right? So I just have these two diodes. Okay. And here again, I'm just using half of the sinusoidal wave. All right, you can count the peaks. 1, 2, 3, 4. 1, 2, 3, 4. All right. All right. Well, that's it. Thank you so much. One last thing I forgot to talk about were the references that I used. All right. So the references that I used. I like this book, Encyclopedia of Electronic Components by Charles Black. Really good book. And those diagrams and pictures I had were from allaboutcircuits.com. So that's it. All right. Thanks again.